Okay, so it's 10 a.m. now, so I guess we can get started. Our first presenter is Afaf Kayet, presenting the effect of denture cleansers on properties of various denture materials.
All right, good morning, everyone, and welcome to my presentation on the effect of denture cleansers on properties of various denture materials. So the objectives of my study were to assess the effect of denture cleansers on the mechanical and optical properties of 3D printed dentures to conventionally compression molded heat processed dentures, such as color stability, surface hardness, surface roughness, and biaxial flexural strength. The materials used in this study involved 3 3D printed denture resins and 1 heat polymerized denture resin. Formlabs printer was used to print Formlabs denture base, and Carbon 3D printer was used to print the Denka denture base and Lucitone digital print, and molds were used for the Lucitone 199 resin. A total of 216 specimens consisting of 54 specimens of each type of denture resin were prepared as discs measuring 12 millimeters in diameter and 2 millimeters in thickness. This was the finished printing job of the specimens. These are the final specimens after polishing and labeling. Specimens of each resin type were divided into 4 groups according to the denture cleanser treatment they will be exposed to. 10 specimens underwent baseline biaxial flexural strength testing. 1 specimen of each group was used for surface hardness testing, and the other 10 specimens will be used for color stability, surface roughness, and finally biaxial flexural strength. 4 cleansing solutions were used in this experiment: Efferdent, Polydent, dish soap, and distilled water. Specimens were stored in distilled water at 37 degrees Celsius in between treatment cycles. They were also rinsed in between treatment and storage. The specimens were immersed in either Efferdent for 15 minutes, Polydent for 3 minutes, soap and water solution for 15 minutes, or water for 15 minutes, as recommended by the manufacturer's instructions. This cycle was repeated 28 times. The color stability, micro hardness, and surface roughness testing was done at intervals at baseline, 8th, 16th, and 28th cycles. Biaxial flexural strength testing was done at baseline and the 28th cycle. Statistical analysis was done using the 2-key HSD test with a significance level of 0.05. Statistical analysis was done with the JMP Pro software. For the color stability, the 3D printed denture resins, the Lucitone digital print, the Denka denture base, and Formlabs had a significantly lower delta E as compared to the heat polymerized Lucitone 199. Looking at the 3D printed denture resins, Formlabs and Denka denture base had a significantly lower delta E value in comparison to the Lucitone digital print. Unexpectedly, the specimens treated in dish soap and water portrayed a lower delta E value at the 28th cycle compared to those treated with Polydent and Efferdent. Since the specimens were stored in the incubator at 37 degrees Celsius in between treatment cycles, the temperature change could have had an effect on the color more than the different denture cleansers. For micro hardness, Formlab specimens significantly showed the highest micro hardness values, followed by Denka denture base, Lucitone 199, and Lucitone digital print. Lucitone digital print had the lowest micro hardness values amid all the materials. This could have been due to the high flexibility of the material, which was observed during biaxial flexural strength testing. Formlabs and Denka denture base maintained a higher micro hardness throughout the experiment, making these materials more resistant to potential surface changes that could affect the integrity and lifespan of the denture. Micro hardness changes can be attributed to alterations in the polymer structure of the resin, which is known as the plasticizing effect. With increased exposure to an aqueous solution, water enters the polymer network through porosities or through intermolecular spaces. Water molecules can expand polymer chain distance and reduce hardness. This effect is more common in porous materials such as Lucitone 199. For the surface roughness, initially Formlabs showed the roughest surface followed by Dentka Denture Base 2, and then Lucitone Digital Print. Lucitone 199 specimens presented the smoothest surface with a significant difference between them. However, with increased treatment cycles, Lucitone 199 had the greatest increase in roughness. The increased roughness of the Formlab specimens can be explained due to its printing mechanism. For biaxial flexural strength, there was no significant difference between the biaxial flexural strength after treatments of Efferdent, Polydent, dish soap, and water. Decrease in biaxial flexural strength values could be due to the temperature effect from being stored in the incubator at 37 degrees Celsius in between treatment cycles. Thank you for attending my presentation. I would like to thank my mentors, Dr. Fan, Dr. Giordano, Frank, and Jay, our lab technician, for all their support and help.
Now I suppose we can take any questions. Does anybody have any questions for our presenter? Okay, I suppose I can ask a question, definitely. Did you expect the Lucitone to have a lower delta E value, like because of the porosity? Like, did you expect that porosity to have an effect on that?
Yeah, so for the Lucitone 199, which is the heat polymerized resin, I did expect that only because of the way that it's processed. Now with 3D printed resins, the structure is a lot more uniform. And then I did have a slide here after I did like an SEM analysis, which does show how the Lucitone 199 has more porosity. So that definitely can affect like the color stability of the resin. And also the way that it's made, I mean, with the monomer and everything, I think that could also have an effect on the stability of the color over time.
Okay, very interesting. Thank you so much.
Thank you.
Okay, I am our next presenter, so I will go ahead and share my screen. Okay, so I am Raquel Mieta, and I'm presenting on the characterization of materials used to produce orthodontic sequential aligners. This project was done also with Henry Lukic and Spiro McGremis. So some background, aligners have been on the market since 1999 after their development by Align Technology, which is the parent company of Invisalign. They offer a more discrete treatment plan to fixed orthodontics, and then direct-to-consumer orthodontic companies like Smile Direct Club and Candide Co. and others have further increased this popularity of aligners due to their lower pricing and then the convenient at-home treatment plans. There are currently no ANSI ADA or ISO standards that specifically address materials used to produce orthodontic sequential aligners, which is kind of what motivated this project. So our main goal was first to research and characterize the materials. We wanted to characterize them by testing their thermal, mechanical, and physical behavior. We also want to verify their most appropriate method to measure the flexural strength and modulus of these materials, as well as publish work in journals that can then be referenced in a standard. So an overview of our research that we've done so far, we tested 5 commercially available materials: Zendura, ACE+, A+, and C+. These materials were thermoformed over a custom aluminum mold using the manufacturer's instructions and using a BioStar thermoforming machine. From our thermoformed molds, we cut 12.7 millimeter by 50 millimeter by approximately 1 millimeter thick specimens using a CNC. And then prior to testing, we conditioned them at 37 degrees Celsius in ISO grade 2 water for 7 days, plus or minus 2 hours. For all 5 materials, we measured the glass transition, flexural strength, flexural modulus, and light transmission. And then for flexural strength and flexural modulus, we actually tested specimens unconditioned as well as conditioned. And for the A+ material in particular, we tested, we wanted to investigate the influence of mold material. So we tested flexural strength and modulus using an ABS mold in addition to our aluminum mold. So for mechanical behavior, 24 specimens of each material were fabricated using our aluminum mold, and 12 were tested immediately after fabrication, while the other 12 were tested after conditioning. And then we fabricated an additional 24 specimens of our A+ material using our ABS mold, with the same 12 tested after fabrication and 12 after conditioning. We used 3-point bend testing on an Instron test system to measure the flexural strength and modulus according to procedure A in ASTM D790. We used a strain rate of 1% and then applied a correction factor on stress for the large support span to depth ratio. So our results for all 5 materials, we actually found that flexural modulus resulted in higher numbers after conditioning. We actually found a significant difference in conditioned versus all unconditioned for all of them but C+. For all materials but plus, the flexural strength testing resulted in higher numbers and a significant difference after conditioning. And then for our A+ material, we found a significant difference in flexural strength between the aluminum and the ABS mold. And overall, the ABS mold resulted in higher flexural strength, flexural modulus numbers when they were unconditioned, and the opposite was true for our aluminum mold. So we had higher flexural strength, flexural modulus numbers with conditioned specimens in our aluminum mold. And the results of this mostly revealed that ASTM D790 is probably not the most appropriate method for measuring these high strain aligner materials. The ACE, the Zendura, the A+, all failed to yield under the 5% strain limit set by ASTM D790. Which kind of meant that some of the assumptions that standard makes are probably not giving us the most accurate results for those 3 materials. We want to do additional 4-point bend testing, which we are currently doing according to ASTM D6272, and our preliminary data is showing that these specimens are yielding before that 5% strain limit, but they are getting pretty close to the 5% strain limit. We also tested thermal behavior. We used differential scanning calorimetry to measure transition temperatures in all 5 materials. We used 2 thermal scans from 20 degrees Celsius to 180 degrees Celsius with a heating rate of 20 degrees Celsius per minute. And we were able to measure the glass transition in ACE+ and A+ materials. However, for the C+ and the Zendura material, we only measured endothermic peaks. They didn't exhibit a glass transition temperature. Zendura also exhibited the onset of a second transition temperature within our heating range. For our physical behavior, we measured the light transmission of aligner material using a spectrometer and a grading sphere assembly. We measured the light transmission from 380 nanometers to 700 nanometers, and our average values ranged from 80.8% light transmittant to 95.9%. So our overall conclusions were mostly that 3-point bend testing is not really the most appropriate method for measuring these aligner materials. Like I said, we are carrying out 4-point bend testing, but we also have plans to add tensile testing as well, just to further investigate what might be the most accurate method for measuring these mechanical behavior of these materials. We also want to look further into the statistical difference between conditioning versus unconditioning in mechanical testing, and also the effect of the mold material. When we started this, we definitely weren't expecting the conditioning to give us higher mechanical behavior numbers versus the unconditioning, or we weren't even expecting like mold material to make a huge difference either. So that was definitely a surprise that we'd like to look further into. We also want to look further into light testing of haze and comparison to ISO 13468 for light transmission versus the method that we're using currently. And that is all. Are there any questions? Okay, if there's no questions, we can go ahead and go on to our next presenter. So I guess I would like to introduce Atsushi Fujimi, presenting new silicone impression material with improved tear strength.
Yes, just a moment, please. Thank you for introduction. My name is Atsushi Fujimi. I am a member of R&D department of GC Corporation. The title is New Silicon Impression Material with Improved Tear Strength. Introduction. Recently, technological developments have improved the accuracy of impressions from intraoral scanning. However, the accuracy of impressions of root canals and mucosal surfaces where scanning is difficult is low. Therefore, taking impressions with silicone impression material is still important in dental practice. Objectives. When taking an impression in an oral cavity with silicone impression material, the impression becomes thinner and the strength is lower. Therefore, the impression in the thin part may be torn off, and the accurate impression may not be obtained. In order to improve this point, we have developed X-advanced new silicone impression material that is hard to tear. The purpose of this study was to evaluate tear strength, which is an index of the resistance to tearing, and to compare it with the existing product Examix. Materials and methods. This is tear strength test. This is based on ISO 341 angle shape with a tonic. For materials, I use X-Advance and Examix, which are auto mix type. And there are also 3 types. Methods first, fill the mold with the material, thickness of 0.5 millimeters long. Second, storing in water and at 35 degrees Celsius for 4 minutes. Third, the test piece was fixed up and down on the universal testing machine. Finally, the tear strength was measured. Sample size is 5 and cross head speed of 500 millimeters per minute. Results. From the test results of the tear strength, X-Advanced showed significantly higher tear strength than Examix. In comparison between each type, I use Welch's t-test. Discussion. Why is the tear strength of X-Advanced higher than Examix? The reason for this is that the amount of nanosilica in X-Advanced is higher than in Examix. Silica's cyranol groups interact physically and chemically with silicon rubber molecules, resulting in higher strength. In addition, the reinforcing effect of the nanosilica is greater due to its smaller particles and larger specific surface area. And the nanosilica also interacts with each other. Methods 2. We check the accuracy of impression. Impression of the resin model were taken. Tray material is heavy body type. Wash material is injection or regular type. Resin model have post crown and MOD class 2 cavity. Yellow is heavy body and red is injection. Blue is regular. The X-Advance was able to precisely reproduce MOD class 2 cavity and post as well as Examix. The spread of the wash type material was good, and the post area was reproduced all the way to the bottom. Conclusion, the new silicone impression material, X-Advanced, has high tear strength, and it's hard to tear. Therefore, it can be expected that X-Advanced is able to take an accurate impression, even in clinical practices. Thank you for your attention.
Great, good job. Are there any questions? Okay, I actually had a quick question though. When you were testing the strength of them, what kind of specimen, like dimensions, did you use? Okay.
Specimen. Yeah, sorry.
No, just curious. I was just wondering, like, because the molds, don't they usually have to be? I mean, I feel like when you are using molds like that, they have such little details that they need to do. Do you think like the mold that you test would make a difference on if those small details in clinical uses would work? That makes sense.
Sorry.
No worries, no worries. Mostly just wondering if the molds that you sample size that you use when you're testing them like differs a lot from the clinical ways used.
メカニカルそれ
Yeah.
Exadvance has nanosilica.
Yeah, very good
So-
presentation. Definitely, if there's no other questions, we can go ahead and move on to the next presentation.
Sorry. Sorry, I don't speak English well.
Yeah, no, it's perfect. Yeah, it was a really good presentation. Yeah, I enjoyed it. I think we can go ahead and move on to the next presenter.
Sorry, thank you.
Okay, thank you for that presentation. Our next presenter is Satoshi Jin, presenting on the aesthetic and mechanical durability of direct filling resin composite.
Okay. Can you see my presentation?
Yes, we can see it.
Thank you. Now I'd like to begin my presentation. I'm Satoshi Jin from DC Corporation. My presentation title is Aesthetic and Mechanical Durability of Direct Filling Resin Composite. This is objective of my study. Resin composite restoration have been widely used in dental treatment. It has been used not only anterior treatment, but also posterior. Therefore, maintaining aesthetic and fiber resistance are important functions for resin composite. Recently, we have developed a new resin composite, Xenial Acco, using non-filler technology. In this study, we evaluated cruiser and toothbrush wear resistance of various resin composites. Material and the cruiser wear test method was shown in this slide. Materials shown in this table were filled in mold and cured to prepare specimens such shape. While applying the roll, collision and slide motion were repeated to acrylic plate. The length of specimen before and after this test was measured, and the amount of wear was calculated. Next, I show toothbrush wear test method. Resin composite material was filled in acrylic mold and light cure. Surface was polished with diamond paste to gloss of more than 90%. Then it was brushed by toothbrush with water and toothpaste. After 12,000 brush cycles, it is estimated for 1 year brushing and measure surface growth. This is the result of occlusal wear test. The most products show wear of more than 10 micrometers. On the other hand, general code show wear of 4.5 micrometers, which was smallest among these materials. This result indicates that general code has highest wear resistance property among these materials. Next, I show the result of toothbrush wear test. The growth of most material except general code decreased to 30% or less than 10% after brushing 12,000 cycles. On the other hand, the growth of general code was maintained at 50%. This growth value is higher than 40%, which is known to look glossy in the oral environment. This result indicates that general code maintains excellent aesthetics even after toothbrush wear. In general, wear and growth can be controlled by particle size of the contained filler. This slide shows illustration of wear and growth of nanofiller and microfiller systems. In case of nanofiller system, maintain flat surface and prevent wear and loss of growth. On the other hand, in the case of a microfiller system, appear large cavity due to vibration and cause accelerated wear and reduced growth. This is SCM image of materials of this study. As you can see, many materials expect general code contain micro-size filler. In particular, Tetric Prime and Clearfield Majestic contain 10 micrometer fillers, which are considered to be caused of wear. Also, Tetric and Omnichroma contain cluster fillers, and the wear of these products is considered to be caused by aggregation strength of the clusters. And surface of ceramics has small cavity, which is considered to affect wear. On the other hand, the SMMs of general code show non-filler structure, and there was no interface of polymerized filler, even though the polymerized filler was contained. Therefore, it maintains smooth surface and keep high growth and wear resistance. This is conclusion of my presentation. General code shows highest occlusal wear resistance and toothbrush wear resistance property. Therefore, it can be expected to have long-term aesthetics and clinical durability against occlusal stress. That's all my presentation. Thank you for your attention.
Thank you so much for that presentation. Do we have any questions for Satoshi?
Yeah, how do you control the polishing surface with the disc polisher?
So please, one.
So when you did polish the composite surface, in the diagram you use a disc polisher, and your surface is flat. How can you control the uniformity of the surface?
Asking the surface hardness.
Yeah, the surface polishing. So you have a disc, okay? Disc contact with the flat surface is just a point. How can you polish the surface with very high uniformity?
General costs have all non-fair systems, so and its product maintain a flat surface. Is it answer for you?
Not really. Yeah, that's okay. Thank you.
Do you have any other questions? Okay, then I guess we can go ahead and move on to our next presenter. So thank you, Satoshi, for that presentation. Next, I would like to introduce Alan Zetso with stress relaxation of denture-based materials.
Hi. Can you guys see my presentation? All right.
Yes, we can.
Perfect. Okay, so my name is Alan. I'm a second-year dental student from Boston University, and my research is on the stress relaxation of denture-based materials. So the objective of the study, as technology advances, digital dentures are becoming an increasingly popular option for patients and clinicians. It is believed that the novel CAD/CAM denture materials have higher strength than the traditional denture material, potentially making it a more durable option for patients. However, such belief has not been fully assessed in literature or by the manufacturers. So my study aims to evaluate the physical elastic property, specifically the stress relaxation of different denture-based material under constant strain. So the methods for the study, 3 denture-based materials were examined in this study. First one is HIPAA denture base by Dent Supply Sorona. Second one is CAD/CAM block Lucitone 199, also by Dent Supply Sorona. And the third one is 3D printed Denka denture base 2 by Denka. 5 bars per group with a size of 3 by 9 by 50 millimeter cube were fabricated from each material. Lucitone block specimens were sectioned using a boiler Isomet 5000 diamond saw. The HIPAA specimens were fabricated by curing the powder liquid mixture in a silicone rubber mold at 45 degrees Celsius for 30 minutes at 1.5 bar and then sectioned. And then the 3D printed specimens were fabricated using a carbon M series printer. After the specimens were fabricated, they were all polished sequentially to 15 nanometer grit using the boiler EcoMat, and they were stored in the water at 37 degrees Celsius for 10 days before testing. So here's a picture of the 3D Carbon M series 3D printer. This is the a block of the Lucitone 199, and this is just the CAD/CAM block that we sectioned our specimens off of. And then after the specimens were prepared, a universal mechanical tester Instron 5566A with environmental control box was used to measure under a 3-point bending setup at a temperature of 37 degrees plus Celsius plus or minus 2. The specimens were loaded to 70% of the mean failure stress of each specimen at 1 millimeter per minute crosshead speed, and the crosshead displacements was held for 10 minutes to allow the stress to relax, and the load was recorded. And here is a picture of how the Instron machine is putting stress on the specimen. The stress relaxation at the end of 10 minutes loading and permanent string after unloading were obtained, and the load relaxation with time was analyzed to fit the combined Maxwell and Voigt viscoelastic model to determine the relaxation constant, capital K, and the retardation time, tau. And then one-way ANOVA 2-key test was used to compare the values between different groups. So here is the model that we used, that I used in the study. Is a combination of the Voigt model and the Maxwell model. And the reason we use two different models is each model is for a different material. So by combining them, it gives us the simplest model to describe the treatment relaxation behavior that we're looking for. These graphs can give a better picture of what is actually happening during the experiment. So if you look at the blue line, you have the instrument machine putting load onto the specimen, and it holds for 10 minutes and then unload. And during that time, you see the relaxation here, the stress relaxation while holding for 10 minutes. And then you can also see the permanent strain after unloading in this graph. Here is the data that we got. So here we got the mean for the peak stress relaxation percentage, permanent strain percentage, the capital K, which is the slope for the Voigt model, and tau retardation time for each of the materials. If you look at the significance here, groups with the same letter are not significantly different than each other. So if they have different letters, that means they're significantly different than each other. And with the data that we got, we came up with three conclusions. So the first one is traditional hippodenture-based material showed the least permanent deformation after loading. Second one is traditional hippodenture-based material showed the least retardation time, but no statistically significant difference was found between the groups. And then last one is CAD/CAM block showed a significantly lower stress relaxation percentage than other denture-based materials. And thank you for listening to my presentation. This is just an acknowledgement for our lab tech, Jay Choi. And thank you for my mentor, Dr. Giordano, Dr. Fan, and Dr. Joe. Thank you.
Great presentation, Alan. Do we have any questions for him? Okay, yeah, so I guess we don't have any questions. We can go ahead and move on to our next presenter.
Thank you.
Thank you so much for that presentation. Very interesting, actually. I really enjoyed that one, especially as somebody who does mechanical work too. Very interesting how different it is from the aligner materials I work with.
Yeah.
Okay, so our next presenter is Mandy Amber, presenting the comparison of polishability of 3D printed denture-based materials.
Hello, everyone, and welcome. My name is Mandy Amberg, and together with my colleague Shelby Brown and our faculty and advisor, Dr. Bennett, we compared the polishability of 3D printed denture-based materials using 3 different additive manufacturing technologies. Our investigation started with the question, is there a way to obtain a clinically predictable method for polishing 3D printed denture materials to the same level of polishability as the conventional PMMA denture material? With the growing trend and convenience of digitally manufactured products, our aim was to uncover the most effective and efficient polishing protocol for 3D denture materials. As many of us know, smooth surface characteristics of removable dental prosthesis is a keystone variable in deterring the formation of harmful biofilms and enhancing the cleansability of the denture. Clinically, the range of acceptable surface roughness is 0.2 micrometers. Therefore, our hypothesis was that all denture materials would be able to reach the clinically acceptable surface roughness. We used 3 different types of 3D printers: the Formlabs SprintRay Pro, and Carbon M2D. Each printer uses resin from the same manufacturer, Dentica. As our control, conventionally fabricated PMMA auto-cured resin samples were provided by the lab Dental Designs. 2 separate polishing systems were utilized, one being the Polish Cream one-step system, and the other being Miltech's coarse and fine pumice with acryluster polishing system. To analyze samples and collect data, a surface roughness tester and beta gloss meter were used. Each of the 3 printers we utilized uses different additive manufacturing technologies to fabricate the samples. Formlabs uses stereolithography, SprintRay Pro uses digital light processing, and Carbon M2D uses continuous liquid interface printing. For our experiment, we made 10 identical cylindrical samples from the different printers, and the lab fabricated 10 conventional samples. They were then placed in a putty jig. 5 samples of each category type were polished using either the polishing or pumice system with a rag wheel until a clinically visible surface polish was reached and a polishing time was recorded. For consistency, only one operator performed the polishing in a random order, while the second operator kept a record of each of the samples' polishing time. Then 3 measurements with the specified devices were taken for surface roughness and gloss for each puck. Data was analyzed using a 2-way ANOVA and Tukey-Kramer statistical analysis. These images show the samples from each group after polishing was completed. The samples polished with polish are on the left, and those polished with pumice are on the right. Now I'm going to discuss our results. This graph summarizes our findings on surface roughness at the average polish time. The higher the surface roughness value, the more rough the sample was, and the lower numbers correspond to a more smooth surface. Looking to the left of the graph at the top green line, we can see that there was a statistically significant increase in surface roughness in the conventional material with polish group than all other treatments. On the right, you can see that there were similar surface roughness results for all materials when polished with pumice. The red circle on the left depicts the clinically acceptable surface roughness threshold of 0.2 micrometers. As you can see, all sample groups except the packing process conventional poly group were below this threshold, thus reached the optimal level of polishability. This graph summarizes our data on surface gloss. Surface gloss is measured on a scale of 0 to 10, with 0 being a totally matte surface and 10 being a totally glossy surface. The graph illustrates that all 3D printed materials had a higher surface gloss when polished with polyp paste over pumice, but the opposite was true with the conventional materials that had a higher surface gloss than all materials when polished with pumice. Okay, we also found that there's a significant interaction between the material and polish type in terms of the amount of time spent polishing the material. When looking at this graph, we can see that all 3D printed materials took less time on average to polish with polish than with pumice, while the conventional materials take the least time out of all materials to polish with pumice, but the most time out of all materials to polish with pola. In conclusion, we found that all denture materials can achieve clinically acceptable level of polishability, but differences are found in what polish system works best for each material and the time spent polishing. All 3D printed materials achieved overall better polishability when polished with polish paste. In contrast, conventional PMMA lab fabricated materials achieved overall better polishability when polished with pumice. We also know that in dentistry and life in general, time is money. So it is important to know which polishing system not only works better, but also faster for each material. 3D printed materials were polished to optimal level faster with polish, and conventional dentures were polished faster with pumice. The goal of this research was to provide and equip the dental community with polishing protocols. It is paramount that as dentistry and materials advance, so do the polishing technologies. I'd like to thank you all for being here today and now be happy to answer any questions.
Did you prepare the specimen in the same size? In the same dimension, I mean?
Yes, all our samples were the same size. Let me.
In the picture, looks like different. Yeah, the PMP group looks much smaller than the rest of them.
It may be just differences in the photograph size, but they were all the same dimensions.
Yeah, if they are not same, probably the result is not very convincing. Yeah, and another question, something I asked before. So when you do the polishing, how do you control the uniformity of the polishing?
We wanted to base this on a clinically applicable situation. So we just did the process of if we were polishing a denture in a lab using the rag wheel and whatever polish we were using so that we could take it back to clinical experiences.
Yeah, if you use the disc wheel polishing, it's still very challenging to make them uniform in that short period of time because you probably just polish a part of this disc. So did you find that the variation when you test, for example, the gloss, or maybe you can test the roughness?
Yeah, there were differences. We took 3 measurements for each and then took the average. There were differences in the values we found, but in a typical denture, you would find different surface roughness and different topography of the denture. So we thought that would correspond to clinical scenario well, because different parts of a denture would be polished differently in real life. But on average, the numbers, that's what we found.
Okay, thank you.
Thank you for your questions.
Do we have any other questions? Okay. Well, if not, we can just go on to our next presenter. Thank you, Mandy, for that presentation. Next, I would like to introduce Yuri Fukuyo with discoloration resistance property of variable low viscosity composite resins.
Thank you for introduction. Thank you for introduction. My name is Yuri Fukuyo from ZC Corporation. And today I'd like to talk about discoloration resistance property of variable low viscosity composite resins. And as you may know, low viscosity composite resins are selected in many clinical cases because of their usability. And there is a high mechanical property product which we call injectable composite resin, and it can be applicable for tooth cusps. For example, the universal flow and the universal injectable from DC Corporation. And the composite resin is known that also known that the discoloration is caused by the color component in her denture inks, resulting in the aesthetics get poor. Therefore, in this study, we investigated the discoloration resistance property of the variable low viscosity composite resins. First, I shared information materials and the test method in this slide. These 4 products from the denture market in showing here is evaluated in this study. Then I'll explain the test method. The specimens were prepared by filling each material in the mold and then light cured in accordance with each product IFU and polished by SIC paper. Then they were immersed in the lead wine and stored at 37 degrees C for a week. And the color of the each specimen in before and after immersion were measured with spectrophotometer, and the color change delta E was calculated. And the results were statistically analyzed to get after one we now number test. And then moving on to the result part. Here I showed each color change in the left side, and its average was 2.7 with GUI and 16.8 with OCF, 10.3 with FSU, and 7.8 with EUF respectively. And they show significant differences in each other. And focusing on the visual inspection I show in here, GUI showed apparently less discoloration compared to the others, and GUI was seen almost no visible color change. This result reflected previous study, which summarized that the color appearances are the almost same if delta is 2.7 or less. In order to verify the reason of discoloration property differences, additional immersion test was carried out with monomers, BIS MEPP, BIS ZMA, and UDMA, by means of the previous test method. And these monomers are mainly contained in each product I shown in here. The result of this test were shown in the left side. BIS MEPP was significantly discoloration compared to the BIS ZMA and UDMA. So focusing on their structures here, BIS ZMA and UDMA contain hydrophilic functional groups. And thus, while BIS MEPP doesn't, therefore, it's considered in this additional test. BIS MEPP achieved high discoloration resistance because of its structure. Then in conclusion, GUI showed the highest discoloration resistance property against lead wine among tested products. And it's thanks to the low hydrophilic monomer as a main component. And finally, it was concluded that the composite resins mainly consist of low hydrophilic monomers can be expected to maintain the long-term aesthetics in intraoral environment. So that brings me to the end of my presentation. Thank you all for listening. It was a pleasure being here today. So any other questions?
Yeah, I had a question actually. Did you consider looking at the surface roughness of any of the materials to see if that would have any sort of impact on the staining as well, or?
I'm sorry. Do you say it again a little slower?
Yeah, of
Sorry.
course. Did you consider looking at the surface roughness as well to see if it would have any sort of effect on staining too?
And we think it also affect to the color discoloration property. So GUI use a nano size filter, so it also affect to this result. We saw that. Is it an answer for you?
Yeah, thank you.
Thank you.
I would
Do we have
like
any
a
other
comment. Yeah, if you turn on the live transcript, yeah, you can see the translation in the script is very accurate. That probably can help.
That's good tip. Thank you for that. Do we have any other questions? Okay. If not, we can go ahead and move on to our next presenter. Thank you so much, Yuri, for that presentation.
Thank you too.
Okay. So our next presenter is Rachel Becker, presenting on the photopolymerization fundamentals and additive manufacturing of a cast mold dental material.
All right. Hello, everyone. My name is Rachel Becker, and I am a senior in chemical engineering at Purdue. And I am going to be talking about the photopolymerization fundamentals and additive manufacturing of a cast molding dental material, which is a project that I worked on in Professor Bowman's lab at the University of Colorado in Boulder. So the use of additive manufacturing and 3D printing is essential to the dental field. As dentistry requires customization for each patient, 3D imaging allows the use of 3D printing for orthodontic aligners, retainers, dentures, surgical guides, and many other devices. So the idea of this project is to use a thiolene polymerization to create a semi-crystalline meltable material. The new material has the ability to be 3D printed and recycled, and with the addition of specific nanoparticles, the mold can be melted away by induction heating. These material properties hold great potential in cast molding dental devices, similar to the wax casting process shown on the bottom right corner of the screen. The biggest advantage of this material is we're now able to have a 3D printable wax material, which can be locally heated to remove the mold. So the material used in this project is based on the thiolene click reaction. This mechanism rapidly forms a semi-crystalline, high molecular weight polymer. These linear polymers are recyclable by reheating and applied to 3D printing due to the fast polymerization and crystallization kinetics. So materials used throughout this project are hexane dithiol or HDT and diallyl terephthalate or DAT, which make up both the thiol and the ene components of the thiolene click reaction. And this reaction was photoinitiated by TPO, and with the use of chromium oxide nanoparticles, we're able to use induction heating to melt away this mold, which I'll talk about in more detail a little later on. But in order to apply this material to cast molding, we need a low viscosity material with a metallic component for the induction heating. And we also need the 3D printing to have high resolution. To achieve these properties, we are able to adjust the molecular weight and kinetics of polymerization and crystallization by adjusting the stoichiometric ratio of the reactants and also the polymerization temperature. So looking into the stoichiometric ratio effects on molecular weight and also crystallization kinetics, on the top left, I have GPC data of the 3 different stoichiometric ratios that we tested. And as you can see, the 1-to-1 ratio has a significantly higher molecular weight than the other 2 ratios that we tested. And this means that the 1-to-1 ratio is also going to have a very high viscosity, and high viscosity is not going to be ideal for a cast molding process, as it'll be very hard to get that melted part out of the cast. So we wanted to focus on the ratios that gave us lower molecular weights. And then looking more into the crystallization kinetics, on the bottom right, I have rheology data with the storage modulus plotted versus time for the same 3 stoichiometric ratios. And A storage modulus of around 3 × 10⁻10 is what characterizes a crystalline material. So here, the 1.2 to 1 ratio gives us a much faster crystallization rate than the other two ratios that we looked at. And if the crystallization rate is too fast, it's not going to work for 3D printing because the layers need a gelation period in between the polymerization and crystallization in order to stick to each other and create an accurate print. So we wanted to focus in more on the two ratios that have sort of a gap between the quick polymerization and the crystallization process. So we found that the 1:1 to 0.125 ratio gave us sort of the best of both worlds with that low molecular weight, as well as a little hump in between polymerization and crystallization. So now looking at the temperature dependence of the polymerization and crystallization processes, on the left, I have FTIR data of 4 temperature samples from 30 degrees up to 50 degrees, and we have conversion percentage plotted versus time. And as you can see, when the light turns on, all 4 of these samples polymerize pretty uniformly at the same rate. So we can conclude that polymerization is going to be independent of the temperature. And although on the right here, we have rheology data, storage modulus plotted versus time of 5 different temperature samples. And we can see that the higher temperature samples of 45 degrees and 50 degrees give us much slower crystallization rate compared to the other 3. So we can conclude that crystallization kinetics are dependent on the temperature at which we polymerize at, and we can use both the polymerization and crystallization kinetics to tune our manufacturing parameters. So now looking more into the actual 3D printing of these materials, we see that our material system is compatible with most commercial DLP printers, such as the Prusa SL1. The set of molars printed on the top right was printed accurately, including the chromium oxide nanoparticles that I mentioned earlier. And these particles give us the control of light absorption through the sample while printing, as well as enable the induction heating process, which I'm going to talk about more on the next slide. So here, in order to actually use the cast molding process, there needs to be a way to melt out the printed mold from the cast. And we can do this through induction heating using the chromium oxide nanoparticles. So on the left here, we see an induction coil with a metallic screw on the inside. And as that coil is turned on, it creates an alternating magnetic field, which heats any conductive material on the inside of the coil. So on the right side of the screen, we have that same induction coil with a 3D printed sample containing 2 weight % of the metallic chromium oxide nanoparticles. And as the induction coil is turned on from 0 up to 95%, we see that the sample in the middle gets heated all the way up to 117 degrees, which is more than enough to melt the polymer system. So this basically proves that the material system can be used for 3D printing, cast molding, with a way to locally heat the mold out of the cast. So in conclusion, we use the thiolene polymerization to create a material that can be 3D printed, and we can also adjust the melting behavior, crystallization rate, and molecular weight by adjusting reaction stoichiometry and polymerization. And then by including chromium oxide nanoparticles, we're able to heat this material and melt it away, but by induction heating. And basically the main idea is that you could use this material system to cast mold and process dental devices. So thank you for listening to my presentation, and I can take any questions at this time.
I have a question.
Yeah.
What type of devices do you think this would be most applicable for?
I would say the main devices could be informing like aligners, like such as like Invisalign or dentures, where you have that 3D printed mold, and then you can use like a thermoplastic or other cast, and then eventually just heat away that 3D printed mold and leave you with the final process. And then I guess like the benefit of this is that we have a melted away part, which could be recycled and used again. And also there'd be more, or I guess we were thinking that there'd be like better efficiency of the process overall.
Thank you.
Hi, Rachel, nice talk. Thank you. And I have a question about the crystallinity. Do you have any kind of test using either DSC or XID to confirm the 3D printed material is crystalline, or how much is the crystallinity? Thank you.
I'm sorry, what was the question?
So do you have any evidence from either DSC or XID to show how much to show whether your material is crystallized or how much is crystallinity?
Yeah, so we did do the DSC analysis. I didn't include that in my presentation because we mainly use the rheology as a way to see how hard the material was after polymerizing. But we did do some of that DSC data and also incorporated photo DSC, but I unfortunately did not include that in my presentation.
Yeah, just curious, the DSC data did show obvious melting point, right? Not like
Yeah.
us. Okay, thank you.
Was there any concern about the biocompatibility with chromium dioxide?
No, we didn't really consider that yet in this study.
If you wish to get any medical device for long-term use intraorally, I don't know.
Oh, great presentation, Rachel. It's very, very interesting. If we don't have any more questions, then we can go ahead and move on to our next presenter, which is Michelle Tang, presenting PVC matrix impression product and thickness effects on underlying composite cure.
All right, can we see the screen?
Yes, we can.
Fantastic. Good afternoon. My name is Michelle Tang and I'm a D2 at the Dental College of Georgia. I'll be presenting on PBS matrix impression product and thickness effects on underlying composite cure. All authors claim no areas of conflict of interest with respect to information disseminated by this presentation data. So as a little background, the bonded functional aesthetic prototype technique has been used clinically in the rapid recreation of complex anatomy and multiple restorations that would typically require a high quantity of time if completed through a direct composite. To utilize BFEP, clinicians first obtain working casts mounted on a folder articulator, then direct diagnostic waxes would be performed to achieve desired anatomy and contours. An impression would be made of the arch with marketed clear PBS materials while held in place with a clear tray. Intraorally, the teeth would be etched and bonded, and light curable composite is placed into the impression. The tray and the impression are then both seated into the patient's mouth, where light curing would be there to set the composite. This light curing step is sequential and be mimicked in our research. Currently, there are available PBS impression materials marketed as clear for this technique. However, there has been no information revealing how well the underlying photopolymerized resin can cure through various material thicknesses. Incomplete cures could alter the physical properties of the material, leading to changes in wear resistance. Thus, the primary focus of our research was to directly assess the effects PBS materials on composite curing by measuring the differences in monomer conversion of flowable composite through controlled thicknesses of 3 popular clear PBS impression materials used for this technique. Additionally, values for this monomer conversion were related as a percentage to when there was no PBS material overlying the composite within these groups. It was hypothesized that PBS materials appearing more opaque to the eye will result in a lower monomer conversion or be less cured at each thickness. Furthermore, conversion with direct curing for 20 seconds through 2 slides or the control group would be significantly greater than the conversion in the series of clinically simulated scenarios. To understand the second hypothesis, we'd have to delve into the methods of our research. The 3 tested PBS materials were the following. Memacil 2 by Kulzer showed a blue tint, GC Corporation's Exiclear was transparent, and Voco's Registrato Clear was a translucent white. GC's Genial Universal Injectable Composite in the shade A2 was also used. In our setup, a 3D printed jig was utilized that would contain a 2 millimeter thick flowable, as shown in yellow. Pre-made PVS matrix of varying thicknesses was placed on top, sandwiched in between two clean microscope slides to preserve a bubble-free environment. A clear tray material was then placed on top, and the ultra-dent Velo Grande curing light was shown from the top, allowing light to penetrate through the layers. Light exposure was conducted in 3 intervals of 10 seconds each to simulate the clinical scenario. The initial light exposure was through the entire setup. The second light exposure removed the tray, and the final light exposure removed the PVS material with the intention of simulating direct exposure intraorally. 5 replications per thickness of material were conducted. A direct exposure of 20 seconds through 2 slides were used as the control group. Bruker's FTIR machine was used to gather data on the bottom of the flowable composite furthest away from the light source. Monomer conversion was determined from the average of 16 scans by analyzing the change in the molar concentration of aliphatic carbenes as a ratio of aromatic carbenes. The change in these ratios over time determined the percentage cure. As the curing process continues, the ratio should decrease as uncured composite resin would typically display a higher concentration of aliphatic carbenes. To illustrate the obtained data, for a 2 millimeter thick PVS material, a time versus percent monomer conversion chart can be formed. The blue line graph represents total monomer conversion, and as the setup was exposed to light, as shown in red, a drastic increase in percent conversion was seen. Data was taken for a total of 5 minutes for maximal composite cure. For each PVS material and exposure, the effect of PVS thickness on the x-axis against percent monomer conversion on the y-axis was plotted. As can be seen, as the number of exposures increases, the cure of the composite at each thickness increases. However, as we move along the x-axis for each material, there does not seem to be any significant effect of the PVS thickness on monomer conversion. In fact, the percent cure detected after 5 minutes at each PVS thickness was slightly greater than the direct exposure control group curing. A 2-factor ANOVA and Tukey test was conducted at an alpha of 0.05. 5 groups were organized based on the results in which the uppercase letters represented PVS materials and the lowercase letters represented the thickness. Specimens within the groups with similar letter identification were found to be not statistically significant, which actually leads us to the conclusions. At this time, there does not seem to be a significant difference in monomer conversion among product thicknesses, which indicates that our first hypothesis was not upheld. Furthermore, the second hypothesis was also not upheld, as monomer conversion after 3 separate 10-second exposures proved to be slightly greater than the control group for all PVS materials tested. The results of the study would indicate that clinicians using the BFEP technique may not have to worry about the effects of PVS and tray material hindering the curing capabilities of flowable composite. It must be noted that all materials used in the study were marketed specifically for this technique, and any deviations cannot guarantee similar results. We'd like to acknowledge all of the companies that supported our study, and thank you so much for your attention. I would be taking questions now.
Hi, Michelle. This is Tim Dunbar from 3M. I really enjoyed your presentation, and forgive my ignorance, but you're talking mostly about PVS, polyvinyl siloxane materials, but in your title, you say PVC as in your learning objectives. What does PVC stand for?
I believe that just may be a nomenclature issue between the groups that we're working with. So we've definitely seen it being referenced as PVC and PVS, but you're correct. We are working with polyvinyl siloxane.
Okay, I guess to me as a chemist, PVC suggests polyvinyl chloride. So just a thought. So thanks. Very nice presentation. Yep. Thank you. Good job.
Great presentation, Michelle. If we don't have any other questions, we can go ahead and move on to our last presenter. So our last presenter is Akhil Ramani, presenting zirconia bond strength and experimental muscle biomimetic primer in wet conditions.
Just 1 second here. All right, hey everybody. My name is Akhil Ramani. I'm a second-year dental student at the University of Pennsylvania. I worked on this project with Rishi Patel, a third-year student, Dr. David Manoli, a prosthodontics resident, and Dr. Fusen Ozer, a professor of restorative dentistry here at Penn. So our project was on the effect of experimental muscle biometric primer on zirconia bone strength under wet and dry conditions. So a little bit of background on resin composite materials. So they're available for both anterior and posterior restorations, obviously due to an increased aesthetic demand for patients. Current primers are not really effective to achieve a successful and durable dentin bond strength between dentin and composite resin, and that's particularly in a wet environment. And that's why in dentistry we've used rubber dams and isolators in order to make sure that there's no saliva present when we're using restorative materials. And this also applies to the application of composite to zirconia. Zirconia is a very highly used ceramic for different types of restorations like crowns, implants, etc. So inspired by a natural polymer that is used by mussels in the ocean, they secrete this catechol group containing monomer as an adhesive to wet surfaces. So that's why mussels are able to stick so well underwater to the various surfaces that are there in the ocean. And so this monomer is being viewed as a possible primer alternative to cross-link in wet environments particularly. So medical researchers have tried to convert this bioadhesive into a catechol-containing synthetic adhesive for medical sealants and also for dentistry as a primer. So the specific aims of our study, it was to compare the shear bond strength of the adhesive resin systems after application of the experimental muscle biometric primer in wet conditions. And the dentin studies are still under trial. So today I'm presenting the zirconia results. And the research hypothesis was that the experimental primer would increase the shear bond strength of the composite resin to zirconia as compared to the industry standard in both dry and wet conditions. And if correct, this would obviously help revolutionize the entire restorative process because now we don't necessarily have to keep so much focus on making sure that the environment is dry. We can kind of undergo the entire procedure without a rubber dam and without any attention to excess saliva. So the experimental setup, we had zirconia that was section sintered and embedded in acrylic resin, and then this was then polished with carbide abrasive and then sandblasted. And a total of 100 samples were prepared and then split into 4 groups. And we had the ceramic primer on dry surface, ceramic primer on the wet surface, and that was using the clear fill ceramic primer plus, which is relatively the industry standard these days, at least in the clinic here at Penn. And then the experimental primer on the dry surface and on the wet surface. And the after primer applications of 10 seconds, the surfaces were air sprayed, brushed with the bonding agent that we use in the clinic, which is Optibond Silver Plus, and then it was cured for 20 seconds. So in the next picture here, I'll show you the entire setup here. So on the left, we have the copper cups that we use, and that's what the zirconia is embedded into using acrylic. And then you can see there's a cylindrical section of composite that is placed on using this apparatus that we have. In the middle, that's what is used to test the shear bond strength. That's just a universal tester. And then on the right, you can see there's a little black apparatus in the front of that picture. And that's what we use to push the composite down onto the copper cups, onto the zirconia, and then we cure that and then use the tester to test the strength. And then the results that we saw that the mean values were actually significantly different for the wet and control groups. So the wet experimental and control groups. We did not see a difference in the dry groups. So we were able to see that the wet surfaces actually did not change the bonding performance of the experimental primer. And so the initial results showed that the pretreatment of zirconia surfaces with the primer may improve the bond strength to the surfaces in wet surface conditions. And so just looking ahead, the Denton studies are still being conducted, but thus far we are seeing very promising results that illustrate an improvement in bond strength in both dry and wet conditions. And then, as mentioned earlier, this is actually truly able to improve the bonding of the dental materials such as zirconia and dentin. In wet conditions, that would open the possibility to a plethora of more improvements in the dentist and patient experience. Thank you.
Thank you for that presentation. Do we have any questions? Okay, I actually did have a question. How did you control like the wet environment, like the wet specimen? Like how did you wet them?
Yeah, so we just actually use standard micro brush that we use to apply the primer in an normal oral cavity. And we just used normal distilled water and dipped it and then brushed on the zirconia for about 5 seconds right before we applied the primer. So the surface was still wet and you could visibly see the water on the surface and then primer right on top of that.
Thank you. Do we have any other questions for Akil or even anybody, any of the session presenters? Okay, well, if not, then I suppose that concludes the polymer-based 2 materials session properties assessment. Thank you to all our presenters and everybody for attending. Everyone did great presentations. And that's it.